This video is brought to you by mywayteaching.com.
So in this part, we are going to start a next chapter. The name of the chapter is Systems of Particles and Rotational Motion. So in this chapter, we are going to study various concepts related to the system of particles and rotational motion. And here we'll study the introductory part, and then center of mass, motion of center of mass, linear momentum of a system of particles, vector product of two vectors, angular velocity and its relation with linear velocity, torque and angular momentum, equilibrium of a rigid body, moment of inertia, theorems of perpendicular and parallel axis, kinematics of rotational motion about a fixed axis, dynamics of rotational motion about a fixed axis, angular momentum in case of rotation about a fixed axis, and rolling motion. So we are going to study about all these in this particular chapter. So let us begin with the first part, that is the introductory part. Okay. Already we studied the motion of a single particle. Okay, a particle which is represented as a point mass, and it has practically the sizes, that particle is having no size. Okay, and even we applied the results of our study even to the motion of bodies of finite size in the previous chapters, assuming that the motion of such bodies can be described in terms of the motion of a particle. As I told you before, the motion of a particle, the body is composed of so many particles, isn't it? So we can apply that motion of each particle while considering the motion of a body. So any real body which we encounter in daily life has a finite size, isn't it? Yes, in dealing with the motion of extended bodies, means bodies of finite size, often the idealized model of a particle is inadequate. If you consider only a particle structure, then it's very difficult to consider the motion of a whole body. So in this particular chapter, we are going to study about those things. Okay, an extended body in the first place, that is a system of particles. So we'll study about those system of particles. The center of mass of a system of particles will be the key concept. And what is that center of mass? We'll study later. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Okay, we can solve so many problems if we consider the bodies as rigid body. What is this rigid body then? Yes, let us see. Ideally, a rigid body is a body with a perfectly definite and unchanging shape. The distances between different pairs of such a body do not change. If you consider two bodies, if if I say they are rigid bodies, which means that their shape will not change and they have a definite shape, and the distance between different pairs of such a body will not change because those size of those bodies will be definite. It's not going to change. So it is evident from this definition of a rigid body that no real body is truly rigid, since real bodies deform under the influence of force, isn't it? But in many situations, the deformations are negligible. In a number of situations involving bodies such as wheels, tops, steel beams, molecules, and planets, on the other hand, we can ignore that they wrap, bend, or vibrate, and we can treat them as rigid bodies, isn't it? In reality, it is not possible because most of the bodies will change their shape when we apply force. But in some of the situation, or you can say in most of the situations, the change is negligible. For example, we can consider wheels, planets, molecules. We can consider them as rigid bodies, isn't it? Yes. Now let us see what kind of motion can a rigid body have. See, let us begin with a rectangular block sliding down an inclined plane without any sidewise movement. You can see that in the figure. Okay, in this figure you can see a rectangular block which is sliding down an inclined plane, isn't it? This is a rectangular block which is sliding down an inclined movement, and this block we can consider as a rigid body. Its motion down the plane is such that all the particles of the body are moving together. That is, they have same velocity at any instant of time. So if you consider this rectangular block, it is made up of system of particles, isn't it? It is made up of so many particles. So all the bodies, when this rectangular block slide down an inclined plane, all the particles will move with the same velocity, and those particles will be having same velocity at any instant of time. So the rigid body here is in pure translational motion. Okay, which means in pure translational motion, at any instant of time, every particle of the body has the same velocity. If every particle of the body is having same velocity at any instant of time, then we call that kind of motion as translational motion. So usually these rigid bodies will be having this translational kind of motion. Okay, let us consider one more example here. Consider now the rolling motion of a solid metallic or wooden cylinder down the same inclined plane. So here we are considering a round shaped cylinder. So rolling motion. The rigid body in this problem is, what is the rigid body here? That cylinder itself is the rigid body. So it shifts from the top to the bottom of the inclined plane, isn't it? When it comes from this point A to B, it shifts from top to bottom of the inclined plane, and thus it has translational motion. But as you can see in this figure, all its particles are not moving with the same velocity at any instant of time. If you consider, like at you can say at point P3, this P1 and P2 particles are moving with same velocity, but P4 is not moving with the same velocity, isn't it? So if you consider at any particular instant, the velocity of all the particles will not be same, but in case of rectangular block it is same. So the body is, therefore it is not pure translational. Its motion is translation plus something else. So here we can't say it's pure translational motion because the velocity of all the particles at any instant of time is not same. So it is not pure translational as okay, but the first one rectangular block, it was a pure translational motion. Here it is pure, it's not pure translational, it's like translational, but it's plus something else is added to it. Okay, so here you can see the rolling motion of a cylinder, it is not pure translational motion. Points P1, P2, P3 and P4 have different velocities at any instant of time. In fact, the velocity of the point of contact P3 is 0 at any instant if the cylinder rolls without slipping. Okay, see, at one particular instant of time, the velocity of this particle p3 is 0, whereas p1 is p2, the velocity of those particles is not 0. So all the particles are not having the same velocity at any instant of time. So this is not pure translational motion. So now I told you, right? It's no translational plus something else. What is that something else now? Let us try to understand what is that something else. Okay. Let us take a rigid body so constrained that it cannot have translational motion. The most common way to constrain a rigid body so that it does not have any translational motion is to fix it along a straight line. The only possible motion of such a rigid body is rotation. If you fix it on a straight line, the only possible motion is rotation. So the line along which the body is fixed is termed as axis of rotation. Okay, if for this kind of, you can get these kind of examples in a day to day life. One simple example is fan, isn't it? A ceiling fan, a potter's wheel, a giant wheel in a fair, merry-go-round, and so all these are the examples. Rotation about a fixed axis. Okay, you can see here. So this is the rotation about a fixed axis where it is having a straight line. You can see here, this one is called as axis of rotation. This one you are considered to understand what is that something else. So here the velocity of the particles will not be same at any instant of time. It continuously changes because it rotates, isn't it? As we saw in case of that cylinder, when it rolls down from an inclined plane, the velocity will be different, isn't it, at any instant of time. Similarly, in this case also, the velocity will not be same at any instant of time. So we are considering this to understand that something else with translational motion, isn't it? Yes. And here we have fixed the fan along a straight line. So why we have fixed? Because in that case the only possible motion for the rigid body is rotation. So the line along which the body is fixed is termed as its axis of rotation. As I told you, in this case the line along which the body is fixed is this line, and this is called as axis of rotation. So this is a very simple example, and one more example you can see here. A potter's wheel. So here also it continuously rotates, isn't it? Again, the velocity of the particles will be different at different instant of time, and this rotation, the no the line to which it is fixed, again it is called as what? Yes, it is called as axis of rotation. It is very much important. So these two are the simple examples. Okay, along with these two we can have, we'll get so many other examples of this kind. For example, you can say a giant wheel that is also fixed, right, at one point, and then it continuously rotates. And a merry-go-round is another example. So along with this ceiling fan, potter's wheel, these two are also very simple examples. So in the next part, we'll try to understand what rotation is, what exactly the meaning of rotation. Okay.